So here we go on Lesson C, electric circuits. We're looking specifically at DC circuits as direct current. In this first video, we'll look specifically at series circuits. We're going to start with looking at schematics of how to draw circuit diagrams, and then move into what are called series circuits. So here we go. So there's all kinds of different symbols that are used when a drawing of a circuit is made. These drawings are called schematics. All the various circuit elements in a schematic drawing have different symbol to them. We got a battery, wires are just lines, a resistor is this little squiggly, a light bulb is a loop with a circle around it. We have a junction, that's just an area where a wire moves from in one direction, and then it's like a little T junction there. A capacitor, switch, and there's all kinds of others that we could have. These are primarily the ones that we will deal with in our treatment of circuits. So let's look at a simple circuit. Our circuit here has a battery, has a switch, and a resistor. This resistor represents the load on the circuit. The load is the thing in a circuit that uses up the electricity. It uses up the energy. The load for a power plant is all the various places on that network that would use the current that's produced, right? The load in a flashlight is a simple light bulb, okay? So a load can be something very complex, or it can be something very simple. Now, in the symbol for the battery, let's take a look at it real quick. There's the line has a long side to it and a short side to it. This long side, this is always going to be the positive side of the battery. This is always going to be the negative side of the battery. Okay, so the current in a circuit moves in the direction of a positive charge carrier. So that would be from the positive side of the battery around the circuit to the negative side of the battery. So the current goes up in this circuit. When the switch is closed, right? So when we close that switch, we complete that connection, giving that current somewhere to go. Current takes a right-hand turn there, comes around, goes through the resistor, drops off some energy there, and goes back into the battery here, where those little charge carriers can pick up more energy and move back through the circuit. At this point, I want to point out to you a really great analogy for understanding circuits and current and load and voltage drop and things. It's in your reading packet. It's an analogy that uses a coal mine as an analogy for an electric circuit. So if take a moment, pause the video, and make sure you read through that part of the reading packet. It should be there on page 11. Okay, so let's see if we can take a circuit diagram like this one here and see if we can come up with a schematic for it. Here we've got a battery, we've got a capacitor, and we've got a resistor. Now typically batteries are always drawn so that the positive side is up to the top and the negative side down at the bottom. You can also tell the positive side of a battery because it's got the side that's got the nub on it. So to draw this circuit diagram, you'd want to follow the direction of the current. Okay, so if we look at this, the current comes out the positive side of this battery and immediately is split into one side goes through a capacitor, the other side goes through a resistor. Once that current leaves that capacitor, this is all happening while that capacitor is getting charged up. Once the capacitor is charged up, the current stops flowing through it. All right, so once the current then leaves that side of the battery, and we meet another junction here at the resistor. Okay, after that junction, all the current goes back to the other end of the battery. Okay, so for the resistor side, the current goes through here, goes through that resistor, and right back. Right here at this junction is where the current that goes through the capacitor meets back up with the current that went the other direction, and it all goes together through that to that negative side of that battery. So the circuit diagram of this circuit would look like this right here, where we've got the battery here, so our current leaves, okay, and in our schematic we've drawn a wire, it's got some length as it comes out of the positive side of the battery. That's just to be able to give us room in our drawing to get to this junction right here. So the first thing that we meet, the first thing that our current meets is this junction right here. Some of that current goes through the resistor, some of that current goes through the capacitor. It all meets back up after the resistor and goes back to the negative side of the battery. So if you're having a hard time understanding how this becomes this, pause the video, rewind it, make sure that you see how this is this. Follow the current. Now, circuits are classified by the type of path that the electricity follows as it goes around the circuit. There's two types of circuits, series circuits and parallel circuits. In a series circuit, there's only one path for the electricity. All the circuit components are in a line connected by the conductor so that all the electrons flow through each component in turn. In a parallel circuit, there are different paths that the electricity could go. Some of the electrons will go one way and some will go a different way. Most circuits are a combination of both, like this one here. So here we've got a series circuit. The current will come out of the battery, go through each element in turn. Here's a parallel circuit where some of the current will go through one side, some through the other. All comes back together into the battery. Here we've got a combination circuit where some of the current will go through this resistor here. The other part of the current will go through this section where these three resistors are series together. Now, each type of circuit has its own set of rules that govern how the current, voltage, and resistance behave. But there is also a set of rules that apply to all types of circuits, and we call these rules Kirchhoffs laws. So first, we have Kirchhoffs junction law, which states the sum of the current entering a junction equals the sum of the current leaving the junction. So when we come to any junction, however much current goes into that junction will leave that junction. So here we've got I1 goes into that junction. I2 plus I3 will equal I1. Then there's Kirchhoffs loop law. The sum of the potential difference across all the elements around any closed circuit loop must be zero. So that's telling us that as we go around a circuit, all the voltage drops will add up to zero. It's called Kirchhoffs loop law. Both of these rules apply to all circuits, okay? But there are certain rules specific to series circuits and certain rules specific to parallel circuits. So let's start by looking at the rules specific to series circuits. So here is a simple series circuit with three resistors, R1, R2, R3. When the electrons leave the battery, now you keep in mind that the electrons actually leave through the negative side of the battery, go this way. We count current as going from positive to negative though, okay? So let's look at the current. So our current goes from the battery, goes through R1, then R2, then R3. The energy that is carried through those charge carriers then is dropped off first at R1, then that energy is dropped off at R2, then that energy is dropped off at R3. Now the same number of charge carriers that go through R1 will also go through R2, will also go through R3. So that means the current is the same in every part of a series circuit. The current through R1 will be the same as the current through R2, is the same as the current through R3. The total resistance of the circuit is equal to the sum of all the resistances together. So in this particular circuit, we've got 3 kiloohms here, 10 here, 5 here. So we've got a total of 18 kiloohms of resistance in the entire circuit. And finally, the voltage provided by the voltage source is equal to the sum of all the voltage drops across each of the resistors. So each of these voltage drops, so as that energy moves through from that battery through that circuit, drops some energy here, drops some energy here, drops some energy here. We call that the voltage drop. Okay, so all these voltage drops will add up to the total voltage of the circuit, which we can see from this diagram here would be 9 volts. Now, on your equation sheet for resistors in series, you'll be given this equation here, which simply says that the total resistance is the sum of all the resistances. And you have to remember then that the current is the same in a series circuit, the total resistance adds up, and the voltage drops add up. Let's take a look at a couple of examples here of series circuits. Okay, so let's take this circuit right here where we've got a 25 ohm resistor, a 35 ohm, and a 32 ohm all connected up to a potential difference of 18 volts. We want to find the total resistance and the current in the circuit. So we're just going to apply the series rule for resistors in series. We add up each resistance and we get a total of 92 ohms for the total resistance of that circuit. Now, in order to figure out the current, though, what are we going to do? What are we going to use to figure out the current? Well, if you guessed Ohm's law, you're right. Since we've got the total resistance of the whole circuit, we've got the total voltage drop across the whole circuit, we can figure out the current in the entire circuit. Okay? So it's the 18 volts is our voltage drop. Our resistance is 92 ohms. We get a total current of 0.196 amps. Okay? Now that works when we're looking for the total current here, but there are times where we're going to ask something like maybe you're given a current and a voltage drop and the total voltage, and you want to find the resistance of a single resistor or something like that, or we want to find the voltage drop across a single resistor. Let's take a look at how to do that. So in this example here, we're given this series circuit, and we're asked to find the current in the circuit and the voltage drop across each resistor. Now, more often than not in any of these circuit problems here, the first thing that we're going to do is find the equivalent resistance of that entire circuit. So we find the entire resistance, we add up all those resistors, they're in series, and we get 75 ohms as our resistance. Then we can simply apply Ohm's law. We've got 9 volts as our voltage for the whole circuit. We're looking for our current, and we've got 75 ohms as our total resistance. Gives us a current then of 0.12 amps. There's the current in our circuit. Now, because this is a series circuit, that tells us then that the current is the same across each one of those resistors. Okay, so each resistor experiences 0.12 amps of current. So we can use that to figure out then the voltage drop across each individual resistor. So to do that, we apply Ohm's law individually to each resistor. Each experiences the same current, and we get for voltage drop across resistor 1 would be 3 volts. Voltage drop across resistor 2 would be 3.72 volts, and V3 is going to be 2.28 volts. Now when you go and add all these up then, that equals 9 volts, which is what we should expect from a series circuit. Okay, so there's series circuits. Next video we will add in parallel circuits, and then after that we'll look at combination circuits. See you in class.